Hey guys. Well, I hope you didn't have too much of a big lunch because I'm gonna talk for 1 hour about build files. Just so I know, like to get a better feel of my audience, who here likes to write build files? Okay, keep your hands up, keep your hands up. Then, who likes to write especially CMake list files? Okay, for those watching on YouTube, that was almost everybody. All right, yeah, I know. It's a pain. We usually think that it could be delegated to somebody else. I mean, for some of my time, well, maybe not me, because I'm like very super into make files and build system, maybe too much. But for most people, I guess, if your manager came to you and told you, I have a way that, I don't know, this external company or this guy down the hall is gonna write all your build file for the rest of your life, everyone would say, okay, great. So yeah, for most of us, it's a problem. It's like a hassle. It's something that we would like to not do. But, well, I started working with that for some years, and I discovered that actually it can have some purpose. For example, did you ever start with like a small application you built where the dependency graph looked like this? Well, it's very simple. You have 4 libs and a simple diamond pattern. You let that live, and after, I don't know, a few months, years, you get something like that. Sounds familiar so far? All right. Yeah, that happens to me too. So, what are we gonna talk about today? We are going to see what's the idea between the theory behind modular design, the idea that you should keep a clean graph dependency and a clear code architecture, and how we can integrate CMake into that. Well, technically speaking, any build system worth its salt should be able to allow you to use some patterns that will give you the same results. I'm just going to use CMake because that's what everybody else uses if I trust GitHub or any open source project, really. But really think of that as just an illustration. Any build system should be able to provide you with the same thing. And in fact, most of what I will tell you today is taken from other build systems, some that are usually considered more modern, that you also can have simply with CMake without the, the big pain of changing entirely your build system. A few words about me. I'm Mathieu. I'm from France. You might have heard it already. I work at Murex, and since 1 year I've been a contributor to Conan, and all I got for my pain was this lousy t-shirt. And, well, along the way I discovered a few things about CMake, about packaging, and about how do we use all that to make better code. So let's talk a bit about CMake. First thing that most people think is that CMake is a build system. Well, it's not. Technically speaking, it's a build system generator. You tell him that you want to build a project, and all it does is generate the build file for somebody else. Make, Ninja on Unix, Visual Studio, or something else on Windows. It just does that. It does not build by itself. It's just a meta description for the generator you use. It's, well, almost 20 years old now, and it's used in lots of open source projects. You might recognize a few, and that's not limited to open source. Private company also use CMake internally. And so, what's the big deal with CMake? Well, basically, it's maybe not the best, but it's the less painful solution we have to handle portability in C++. Because the language can be portable, your libraries can be portable. If your build system is not, if you have to write, like, again, your build files for every system, you're not portable. And what CMake does is that you can finally write the thing once and have it work everywhere. And as we all know, it was a big success. For example, if you want to invoke it on a Windows machine, that's how you do it, and on a Unix machine, that's how you do it. All right, almost portable, I would say, but we're not so far. So what do I call modern CMake? You might have seen that that was the title of my talk. I'm not entirely fond of the title myself, but you know, there's modern C++. Why not modern CMake? It's something that's been available for some time. The first, I would say, first compatible release would be 2.8.12. But in practice, a few months after that, they moved to the new 3.0 release, which has a few more features, but exactly the same philosophy. And it's very important to note that it's 2.8.12, because it's not a patch release. They changed that in the new 3 branch, but in the branch 2, the last one was also a feature release. It's not semantic versioning. So when I say 2.8.0 and 2.8.12, there is like a huge array of features that you're missing between the first and the last revision. So how do I know that any project I open on GitHub is not using modern CMake? Well, that's easy. I just have to look at the top line of your project, and I see require 2.8. None of the features are guaranteed to be available. Even more than that, if you can have them because you have a more recent CMake, CMake may disable them because he wants to be compatible. That's what you are telling him. And that's how, well, yeah, that makes me sad because you're missing out. Let me explain exactly what you're missing. What you're missing is the opportunity to have your build system help you do a better design. But before I explain that, let me go back to what I call modular design. The idea was taken from John Lako's talk that I had the privilege to watch last year. 3-part talk, very interesting, like 1 million slides in 3 hours. It comes from his book, which is about the same length, I think like 1,000 pages. And I will try to summarize what I've taken from that for this purpose. So obviously it will not be everything because that's like a huge topic. And John, if you're watching this, I'm sorry. I'm going to make mistakes. I'm going to forget something. But the idea is there. I hope so. So to explain modular design, I think the best idea is to take a simple example. Imagine for a second that you join a small startup. There's like maybe 2 or 3 developers, and you have this big idea that you are gonna provide a service to compare and find the best taxi ride in your region. So you have this first iteration. You have to deliver a minimal product just to demonstrate your nice algorithm to your investors and obviously get some money and get funded for the rest. So if you try to apply some kind of modular design rules, you try to keep concerns separated. So we'll have a first library that will handle the taxi prices, the description of your objects, and a few operators to manipulate them, maybe make sums or comparison, whatever. You will have a second one that we'll use to describe a client order, like what's his name, what's his profile, where does he come from, where does he want to go, that kind of stuff. And the final is the fare, which is the result. That's just a very schematic example. But the idea is that to build your calculator, you actually depend on 3 modules which are completely independent and that you can test even without your super nice algorithm. That's the point. So that part usually we get it right because it's like 4 libraries and we are like 2 developers. Some time passes, you see your investors, they are very happy, and they say, all right, go for it, develop me a full service now. The proof of concept was okay, here is your funding. Okay, so you have to talk to the rest of the world. So first you write some kind of a JSON parser that's able to retrieve the prices from all the companies in your area. Okay, then you want to serialize your clients' orders, so you had some SQL database, and you had a library to do the serializing. Note that at each time, we decouple the problem. First, we have the technical dependency on the JSON, on the SQL library. I still have the class that represents my object, and then I have one library that combines both. The idea is that I can still work with them in isolation. If tomorrow I decide that SQL is not the future, that it's NoSQL, or that it's whatever, I can change that with no impact on the algorithm, on what it's making my company money. And of course, we finish with another serializer for the output of our algorithm in JSON. Okay, we're still fine. We have followed the practices. Again, we're still a small startup. That's fine. Okay, we scale up even more. Our clients are very satisfied. We can finally put all that in one nice service. So we had a dependency on a REST server library, which itself is using some HTTP library. And we create at the top the simple router that takes a request, check the prices, and gives you a JSON response with the best price you can get for what you ask. With me so far? Okay, that's a theoretical example. That's maybe what you might have seen in some classes. But then there's practice. And in practice, well, it might look more like this. You had some dependency that are kind of dubious because you had to, maybe you were in a rush, or maybe you just didn't notice it. It just went through a code review, or you were tired. Well, we have lots of excuses, or I guess we give ourselves lots of excuses. Anyway, in practice, your code is not like this because you have circular dependencies. So in practice, your two modules are only one here and one there. So directly, if you start looking at your graph, it's not that good. You start to have a mix of concerns, things that are not really in the same domain, that are bundled in the same library, and you cannot already test one without the other. So, well, it's starting to get messy, but you can still test most of it. But in practice, if you let that pattern go and go and go, you end up with something like this, which is one big blob, which is your service, and then maybe a few external libraries, and if you're unlucky, you may have even circular dependencies between your third-party libraries or the things that you consider really technical. Does that sound familiar to anyone? Okay, all right. You were silent. I had a doubt for a moment. Like, is that only me? Right. Now I'm convinced. All right. So what's the idea? The basic idea behind modular design is just that you keep control of your dependency graph. You make sure that when a library needs another library, it's explicit and it can be checked by some kind of tool or reviewer to ensure that you are not creating a monster, that you are not going through a huge monolith with circular dependency, with nothing you can reuse or test in an isolated way. And of course, without so much cost. In this example, you cannot reuse anything of your nice algorithm without the whole stack. In this one, it's still possible, and the furthest we go, the better. And then there are modern build systems. They came back. Well, I'm not sure which one I would call the first one. We might have heard about Bazel at Google, or the other clones that came out afterwards, like Puck or Pence, whatever. They all have the same philosophy behind them, is that they are very explicit in what you say. You are really explicit about what you ask to in terms of build. You only ask for what you use, and the system will forbid you to use something that you did not declare. And that's the key. If you do not declare something but you can use it, you will have a problem, because it will slip through at some point. And that's exactly the idea of a modern build system. It's that it protects you against bad patterns, and it helps you leverage on that to make sure that you keep a clean architecture. So if you come back to CMake, what will happen? What happens today in most projects, in what I call, well, not so modern CMake? If I try to build, like, I don't know, a small project with just a TCP client and its own TCP library. Very simple, two libraries and one library, one executable. That's it. Well, what do you think of that? Does this sound like something you might have seen or even written? Seems okay. Well, first thing, I had a subdirectory, which is my library. I declare an executable. I add the necessary include directory, possibly some flags if I need like IPv6 in that case. And then I tell CMake that my binary depends on the library. And the problem with that, the problem with that is that I'm not expressing myself in terms of modules here. I'm not saying CMake, I have this binary, it needs this library. I'm telling CMake, I have this binary, it needs those headers, it needs those flags, and then it needs to link to that. I'm not talking about modules. I'm talking about build flags. And there is a world beyond those two. You can miss a lot of things, and it doesn't scale. If I build up on my TCP library for another project, and I want then, I don't know, an HTTP library and then a REST library, what will happen to my build flags? Well, TCP is quite clean. I just have -i TCP and -d IPv6. Then I do the lib HTTP. I have to copy-paste those flags plus the flags for the library itself. And then again, same thing for the library just up ahead. And it doesn't scale. Every time you have a public dependency, that means that you would have to take all the public flags from the library you're using and copy them in your CMake list. And if you go to like 3, 4, 5 iteration, you end up with like, I don't know, 3 lines of flags that you have to add to your library or to your program to be able to compile. That's what I'm afraid that's what I see in some projects. And what do you do usually? You just give up, because it's just a nightmare to maintain. If you have to change the library that's at the root, you have to modify everything in your system. So what do? You go to the top CMake file and you say, all right, everybody can include that directory, everybody can link to that, done. And that's the only sane way you can, well, that's the only sane way you might think you can do it. And I won't blame you for that. I did the same thing. And the idea is that CMake has another way, and most build systems have another way. Because if you're thinking about flags, you're not thinking about modules, you're not thinking about architecture, you're just thinking in terms of -e, -d. It's a mess, it has no sense. There is no way for you to try to reason about it and think about, all right, am I including this stuff? Is there like a good reason for it? Or am I just, I don't know, grabbing things that I should not, things that maybe depend on me while I'm depending on them? How can you know? How can you tell? Personally, I can't. The other way around, if you just declare modules, if you just say, I have like lib B and it depends on lib A, even if you scale that to like 100 or 1,000 module, I mean, every intern at your company can take that, do a grep, output that in a dot file, and just draw you the graph. And I'm pretty sure it's easy to write some kind of sanitizer or a check tool that you can run on your Git commit or on your pull request to tell you, all right, you've introduced a circular dependency, you cannot do that. If you reason in terms of modules, it just becomes a graph. If you reason in terms of a huge list of flags, well, you can't do anything. You're stuck. So the idea behind a modular, a modern build system is simply to protect you from for circular dependencies, or at least tell you when you're doing it. You might, I don't think you could have a good reason, but some of them will let you override that if you really need to. Of course, like I said, the idea is that you can reason at module level. Really, not talk about flags. And basically, it means that the build system is doing more than when you're telling him. It's not just a script file that's doing blindly what you're telling him like a dumb robot. It is trying to make meaning on what you're building and say, hey, I'm not in your place, but if I were you, I will not do that. I'm pretty sure you're not doing what you should be doing. The same way your compiler can tell you, even if it doesn't stop you, that you are returning, I don't know, the address of a local variable or something else that in 99% of the case is a bad pattern and that you should avoid. So in practice, how does it work? It's simple. Each module will define, of course, the build flags it needs because, well, you have to define them somewhere. They're not going away. They're just localized. You just tell, all right, this is my module. This is what it needs to build. Then you say, all right, this is what I require. This is the dependencies I use. But you talk about dependency. You don't talk about flags. you do not look at the other modules internal. That's not your concern. You just say, I want lib B, give me the flags I need to compile and link with lib B. I do not look at the build file and say, okay, in that case, I may need to put that flag because I'm using that feature. That's not maintainable. Of course, you need to split your own build flags in two sets, private and public. That's exactly like the object concern of implementation versus interface. Your private flags is your implementation, the flags that you need to build, but once you're built, you can throw that away, nobody cares. You just needed that to get a binary. The second set is the public ones. It's like your public includes the define that will affect your compilation, all that stuff. And that your clients will also need to be able to compile. And of course, the interface is soft transitive. That means that if you have a private dependency, you take their modules, but then it stops. If you have a public dependency, it adds to your public interface. For example, if we look at what we had in previous example with TCP, HTTP, and REST, it's all public dependencies. So the flags have to be repeated at each step. If that was a private dependency, it would stop at the first consumer because he needs them to build, but then since it's private, it's not seen by the rest of the world. The rest of the world does not need to have those flags to build successfully. And of course, you still have flags. I mean, you have a restricted set of flags. You only care about the flags you will use in your module, but you can still put them, all the ones you still used in the past, you can still have them. And I'm not telling you to stop using flags at all. You still need them. I mean, dus minus E, dus minus W, whatever, you still need them. But you need to localize them. You need to make sure that it does not escape your CMake file. So all that is nice, but how about CMake, right? That's nice. I show you something that's taken from like theory, like maybe some nice system that's going on at another company. But you are using CMake. I am using CMake. I'm publishing stuff on GitHub. Can I use that with CMake? And I would not be here if the answer was not yes. You can. There is actually an answer. What's the idea? The idea is simple, really. Well, you still use the old add library, add executable. That part is still the same. I didn't have your familiarity with CMake, but I hope that everybody is clear on that so far. Okay, great. And then every time you have to put some flag, you use the target variant of whatever you need to set some flags. I will give some details after that. Then, if you want to declare dependencies, you use target link libraries. It's helpfully named because if you want to link with like a direct library with a path, and if you want to link with a module with a project and take its interface, it's the same syntax. It's really a limitation of CMake. I wish there was another keyword so that you can distinguish between those two. There's not. So yeah, it's called target link libraries, but in practice, you're not just telling me CMake that you want to link to a library. You're telling CMake, I'm using that dependency. Please give me all the flags I need to build successfully. And of course, every time you have to specify a property for your files or your build files, you say if it's public or private. Let's see an example. Okay, first part is easy. You start by requiring at least, well, technically you could put 2.8.12, but I think 3.0 is not something too big to ask for most of the world. It's 5 years old now. You should be fine with that. Of course, you can go crazy. You can have 3.9 if you want. I won't stop you. On the contrary, there are lots of interesting features in that. But at least 3.0. Then, well, first counterexample, you might still declare some flags at the top level. Why? Well, that comes from my experience And in my experience, there are some kind of compilation flags that you do not want to localize for some particular module. You want to put them everywhere. And the most important is anything that's a combination of W error and W something. Because there is nothing worse than changing your code and having it break because in your header there is something that will not compile in one of your clients because he's more strict than you. I don't know if it happened to you guys, but it happened to me a lot of time, and that's very painful. So I said that some flags might still be better off at the top level to make sure that all the project is on the same page. And I would ask the same thing for anything that affects the ABI, like a standard level or that kind of thing, because if not, you will get some incompatibilities. All right, then you still do your hard library, nothing fancy here, the same thing you've been doing for, I don't know how much you've been using CMake, but that part doesn't change. All right, and now we come to the meat of the thing. First, you want to declare some public headers. So you say, all right, target include directories, you say it's public, and you give the path. That tells CMake, all right, in the build interface of my project, anybody who wants to use my project will need this include directory to find my headers. If you have some public headers, for example, in your SRC directory, you just add the same thing with private. You'll be able to include them in your project, anybody else won't see them. If you have some settings, something that depends on the config of CMake, whatever, you can also put them with the compile definition or whatever. In this case, it's a public setting, but if it would have been a private setting, you would just have said private instead. That's the same idea. If the setting will have an impact on your public headers, like change the size of a structure or maybe hide some declarations, you need to make that public. If it's only internal detail, like I'm gonna use this algorithm internally or that algorithm, and that doesn't change your API or your implementation, your public implementation, you can put it private. It's fine. And of course, then you have to declare your dependency. And again, I'm sad that there is not a special keyword that's different from the old one to express that. But trust me in that, if I say target link library something ABC, and ABC is a project, I will get all the public flags that are declared. I will get the link flags I need, and that's recursive. If I need transitively some include flags, or some link flags, I will get them. It will even go across static libraries, because as you already know, I think, static libraries are not linked. So if you have a dependency inside a static library, CMake will remember that, and the first shared library or executable that it encounters will link to it. It's taken care of for you. And of course, if you have a private dependency, like something that your implementation relies on, but it's not visible through your headers, you can put it private. It will work too. And it will not be seen by your consumers. Meaning that, for example, if you use Boost, but if you do not want the rest of the world to see Boost, or if you want to make sure that the rest of the world will not use Boost unless it's declared, you make it private. And only people with explicit reference to it will see it. And that's a huge point, because what happened a lot in my experience is that everything that can be found through auto-completion inside your IDE will get used by people, even if it's not publicly declared, but it's available through transitive dependencies. So the less you have in your public API, in your public interface, the more private you got, you're sure that people will have to be explicit about them, and you reduce the risk that your architecture will start to go bad, like I said in the first slide. If you got a header-only libraries, which is kind of the fashion today, you can simply declare an interface library. Interface is a peculiar keyword in CMake that tells it that something belongs to your public interface, but should not be used to build your library, of course, because it's a header only. You have nothing to build. So if you have nothing to build, but you want your clients to see it, you make it interface. And you can even link to something. You can say, for example, my header-only libraries will need this client to be linked to that. You can add a link dependency, it will work. CMake will take care of everything. Because that may happen. You may have a header-only libraries that needs something that's not header-only. It will work. Like I said, nothing to build, think interface. Now that we've seen most of the good patterns, I want to take just a few seconds to recognize the anti-patterns, the bad things. That's the kind of thing when you open a CMake list that tells you that you probably need to rewrite it a bit. So of course, everything that affects all targets, like include directories, add definition, link libraries, those kind of things are evil. If you put them on your top level, everybody in the world will be able to use them. Everybody in the world will be able to include that headers. And if for some reason the code does not require a link, like for example, header-only libraries or inline, templates, whatever, you will not even get a compiler. People will start creating hidden dependencies through other modules, and they will not even see them. Of course, link libraries, I think CMake have told people like for 10 years now to stop using it because it just means every project in the world should link that. Well, I'm not sure anybody in this room will be using this, but just in case, don't. Okay, then, yeah? Yeah, I know. Only the targets and you declare in this file and all the subdirectories you include. Unless you start a new project.
Right, so use those macros, they're okay to use if it's a subdirectory.
I will not, well, I will not say it's okay to use at any point because they will not affect your interface at all. So if you declare any include directory, for example, that your clients will also need because, for example, they appear in your headers, they will have to copy-paste that also to be able to work. I really not recommend using that at all. Well, I will be happy to discuss that with you afterwards because, frankly, I've not seen them in my career. Maybe for a very small project, just like, you know, the test or something, for that, yeah, but for a huge application, that's coming to bite me at some point. And I will get exactly the same warning against using target include directories to include anything outside your project. Because if you include something outside your library, well, you're breaking the rules again. You're not trying to use a dependency, you're trying to use headers from somebody. You're trying to pull something that's not yours to use it without declaring explicitly I have a dependency to that module. And then you're breaking the rules of talking about modules instead of talking about implementation. And that's the thing here. What I encourage you to do is to declare dependencies to modules, not build flags, because it's awful to reason about at scale. Since target link libraries is an old macros, and since CMake did not make a new one, you can forget to put public, private, or interface, and it will work. Which one of the three it will do if you do not put public, private, or interface? To be honest, I can't tell you without looking at the doc. So my recommendation is do not use it. Just always tell if it's public, private, or interface. And of course, target compile option, I would recommend you to use caution, because if you put, like I said, some W error, you might have surprises because your dependency changed and they do not have the same level of pedantic as you do. Or maybe simply you do not use the same ABI, like, I don't know, you ask for C++11, and for some reason another library has for C++03, you do not use the same runtime, you're gonna get into trouble. So I would keep that at top level. All right, if you remember this, I think you get like maybe 90% of what I call modern CMake, because You started working with, you got away from the flags, you got away from looking at the bits and the implementation of other modules, and you move to another layer of abstraction. You're really thinking in terms of modules, in terms of what is my implementation, what are the interfaces I use. You do not care about how people implement their modules. Because another problem is that if they change, you have to change too, unless you declare dependency, and then the build system does that for you. And that's the whole point. And since we have some time, I guess we could talk about the rest, because of course the 10 last % are least used, but might still come handy to you. The first example, and I think the most common case that I did not address yet, is external dependencies. Because we all use third parties, I think, or most of us use third parties, and well, they are not always built with CMake or not always built with that instance of CMake you're running at some point. So you have to grab some packages. For example, here I needed gtest. I read the doc about the find package of gtest, which said that gtest should be built with threads because on some platforms, on some compilers, you need to link with threads too. So I require also the thread packages. Then I create my executable, and since gtest provide me some nice macro, I can add the gtest include here to my directories, and I can link to gtest. And that's wrong. Yeah, that was a trap. Yeah, the problem is that you are falling back to the old flags approach. You are not telling CMake that you are depending on gtest. You are telling CMake that you want to include gtest headers, that you want to link to gtest, and that you want to link to gtest dependencies. And should that change, you have to rewrite your code. And fortunately for you, CMake heard that. CMake saw that, and in the most recent, in the recent versions, they changed their finders to be able to export targets too. So now, if you take at least 3.5, for example, with gtest, you can just say, all right, require gtest, which is the name of the and gtest main, if you want to gtest to generate the main function for you. And that's done. It will require threads for you if you need them. If gtest implementation completely change tomorrow and require something else, it will also take care of it. You will not have to change anything. There has been some effort, like I said, in CMake to add some new finders. The first one was OpenSSL in 3.4. Yeah, that took 4 releases to think that third parties were an issue, but we are getting there. 3.5 was big. We got Boost, we got gtest, so already I guess like half the dependency I require on a new project are there. You got some graphical libraries. 3.6 bring us pkjconfig, which is pretty nice because it's not just find pkjconfig. It's like if you use CMake to find a PC file, it will automatically translate that into a CMake project definition for you. So you can just say, okay, I require that PC dependency. You're all set. Any pkjconfig package installed on your system, you can require it with modern CMake just with that patch, which is, I think, pretty cool, at least on Unix. The only problem is that I never seen anybody using PC on Windows, so that's not exactly portable, but, well, on some environment, that might really be handy. And more recent version, we had OpenGL, OpenCL, BZip, and all that kind of stuff. So yeah, if your manager is a bit old on CMake, if your infrastructure is a bit old, all the more reason to you to ask him to move to a more recent version. You have all the finders set up for you, and that will simplify your code. But what happens if there is none? Because as you have seen, there are some of them, but I don't think that's the whole C++ package community here. Well, I think some of them may be missing. So what do you do? Well, first option, obviously, you can just contact the maintainer and ask him nicely to provide one. You may or may not have some results. You may also have some arguments. For example, you can tell him, as I can tell you today, that if he builds his package with CMake, he just has to add a few instructions at the end to ask CMake to generate that finder for him. Because when you do make install with CMake, you can also tell CMake to generate a .cmake file that will act as a finder. I think Daniel Pfeiffer did a nice talk on this and a lot of other things on CMake at C++ Now back in spring, and it explains all of that. Of course, if you are publishing a library, I encourage you to do one, even if it's not with CMake. If it's with CMake, it's simple. Really, you just have two instructions and it generates them for you. If it's not CMake, well, let's see. It's not that hard. What do I have to do? Well, first of all, of course, I have to do find library to find the library to just make sure that it's installed on the system. And CMake will take care of the question that is it Windows or Unix? Do I have to have a .dll or .so or .lib depending on the platform? You can tell CMake that you add the library as an imported target. And then you say, all right, I want to include those directories and these dependencies, and I have a nice build interface with an external project. Easy. Well, almost too easy. I hoped that by writing that, that would have worked, but it didn't. Turns out that CMake maintainer left me a little surprise in that, and that it's a bit more complex. For internal reasons, you cannot use target whatever on an imported target. Doesn't work. The CMake will throw you out. Fortunately, it's only a wrapper. The target whatever is just a wrapper. It's just telling CMake, go to the list of variables that are defined in my package and set some values. So you can do it by hand. I won't say it's pretty, like you can see, but it does the job. Simply, you still add your library. You have to set a property for the location. You cannot directly tell that when you add the library, but you can just set property. And same thing, all the things you set like public or private or whatever, it's just a set of variables that's added to your project. That's how it works with CMake behind the scenes. That's not even relying on implementation details. That's something you can find in the CMake doc. That's not something I recommend you to use, but in this case you don't have a choice, unfortunately, until maybe CMake patches that. But, well, okay, it's not pretty, but it fits on one slide. So, well, that's not that terrible. Can we have easier alternatives? Well, yeah, there are some. There are some, but as some French famous mathematician said, it doesn't fit on the margin of this talk, so I won't be able to give you all the details. Still, like I said before, Daniel Pfeiffer did a very nice talk about CMake, which is called Effective CMake, I think? Yeah, Effective CMake. It was in Aspen, C++ Now. It explains lots of things about CMake, from generating finders to using CMake to set some compatibility flag for you, checking the standard support, whatever you name it, it's got it. I think it was voted like most helpful talk of the whole convention. So I really encourage you, if you're into CMake, if you have to use CMake, just go look at it. You will see lots of interesting things. All right. So to summarize a bit what we've seen today together. First things, what's modern build? Modern build is about keeping your flags to yourself. Do not try to expose your flags in the code of the others. Do not look at the code of the others to try to get their flags. Just keep that to yourself. It's your private bit. It's your problem. CMake will handle the rest. You think in terms of modules. Really, you think about a graph. You know, it's easier when you think about it. It's just like take a whiteboard and do some architecture like we all like to do when we start a project. and then we fall back into flags because we are out of time. But the idea is that with that you can still do that the whole time, the whole life of your project. You can always go back to, all right, let's put that on a whiteboard, let's make a nice dot file or whatever, and see, okay, does that architecture make sense? Or am I trying to insert circular dependencies or hidden dependencies? And all the rest, all the transitivity, all the hidden flags that you need to pull, you let the build system do that. Again, I'm talking about CMake here, but I don't know what you use at home. Anything should be able to handle that. If not, I guess it's time for a feature request. So for CMake, first of all, take 3.something. The most recent, the better. As you might see, as you have seen, there are some nice finders to this. Use the target something alternative for macros. Unless we are talking maybe about compile option, but other than that, use the target alternative. Always specify if a property is public, private, or interface. You are trying to expose something to CMake, it needs to know the level of visibility, the same way that when you put something in a class, you have to wonder about, is it public, private, or well, it's not protected in that case, but is it public, private, or both? And of course, you have to link against the target to get all these properties. It's still not pretty. I would gladly like to have, like, I don't know, target, require module or something that sounds more like effectively what we are doing, but it's what it will do behind the scenes. It's not just, I want to do -L that library. It's more than that, and it's what you should do. For external packages, well, your first option is simply to use modern finders because some of them are provided. If not, write them, ask the manager to write them, or if you cannot, well, there are some options. Like I said, CMake can generate one from you just by the build definition of your project when you run the configure and the make install. It can do that for you. If it's an external system, you can ask the maintainer, please, could you use, could you write a finder for CMake for me? If it's a PC file, it's automatic. And if none of that is possible, well, I guess you can try a package manager. All right, thank you all for coming, and I think we have like a bit less than 15 minutes for questions. So. We have 2 mics. I think it would be better for the audio if you can come down and.
Yeah, so one pain point for us has been some of the find packages that return hard paths for the library, and then if it gets built somewhere else as part of a different build closure, that path is now wrong due to things like symlink farms. So, like OpenSSL has at some point been an offender in this. So how would you recommend us be able to take advantage of dynamic libraries like that without breaking the build further down?
Well, I'm not sure I get that, because when you run find library, it tries to look for a file, so it should not return if it's not found. You know, you can add the required, and when you do find package, you can tell required, and if the finder fails because the library isn't there, it will stop. I don't know if that's your problem.
So say you had 2 libraries. The first one got built against OpenSSL.
Yeah.
And it had the actual link on the path to the host for OpenSSL that you linked against. And then it goes off to another section in your build fleet. There's another large section of symlink farms that are built. That path is no longer the same. So when you go to link against project A, the path no longer works and you have linker errors.
You're talking about 2 different instances of CMake here, right? Like you do a first run of CMake, you produce some libraries that have some dependencies, and then you import them into another CMake instance. Mm-hmm. Well, I would tell you that's what package manager are for. Really, I would suggest you to look at what exists and check with that, because doing that by hand on the same machine it's possible, because you can you can use submodules in CMake and have everything on the same place. But if you build in different stages, I really encourage you to look at package managers, because if it's just one step, it's possible, but as you illustrate, if it's a few steps, it gets a nightmare to handle recursively. And the easier way, if you want to make sure that you keep everything and that the packages are really cuttable, it's much easier to do with a package manager.
Okay, thank you.
You said something about keep your compiler flags to yourself. I cannot appreciate that more. I mean, that is a complete such truth, because a couple of weeks ago we have a whole bunch of external libraries, and a couple of weeks ago we upgraded one of them, and unfortunately in one of their latest, their most recent version, they have a compiler settings file in which they have declared their compiler flags as public. Now so I built the externals and tried to build our code base, and they had no exceptions in there. Yeah. And so our solution, I mean, my quick and dirty solution was go to the compiler settings.txt and do a CMake string replace all of it except no exceptions and replace them with empty string. Yeah. That was ugly, I know, but is there a better way to do that?
Well, my suggestion would be that first, if possible, do not set inside the CMake list, do not set compiler flags. I mean, do not set like -std. You can like as CMake, is this compiler with the flags I've been supplied able to use C++14 or whatever? That's okay. You can make checks. But I think you should not try to set things. It should be delegated to the invocation of CMake when you can do -d, CMake, CXS flags, etc. And then you can have a profile that you use to invoke CMake, but that should be external. I don't think you should store inside your CMake list flags that define the ABI, the binary compatibility, because of course, two libraries will have their own set of flags, and they will disagree, and it won't work. It should be possible, it should take something external, some external input, to know what kind of runtime or what kind of -std it should be compiled with. It should just make checks. Okay, is it possible with the environment you supply me to build or not? And fail if you cannot, but not try to hijack the process and decide that you will change the way it was supposed to be built.
So the external library itself builds fine. And we built that with their own flags. But since we did fine package on that, I think the flags leaked into our builds.
That could be this. If some public flags are like, I don't know, some -d. That's what I said when I said do not use compile flags inside. Do not set compile flags in targets. For me, compile flags that are very platform and infrastructure, it belongs to a profile that should be shared by every CMake project you build in the same environment. You should not keep that inside CMake. I think it's a bad idea. You're just setting up yourself for disaster.
Okay, thank you.
Hi. So could you go back to your example of using Boost through the target?
Yep.
I own an open source library.
I think I can. Yeah, there is one
Perfect.
here.
Right. So I own an open source library, and I recently wanted to upgrade to use modern CMake, and so I switched to using the targets created by the find boost script that comes in the box with CMake.
Yeah.
Then I updated my boost version to the latest boost version the day after it came out, and then my library didn't work anymore because CMake refused to generate targets for the latest boost because it does not know. My belief is that it's because it doesn't know the dependency information between the boost libraries, and so it doesn't feel confident in creating all of the targets because it doesn't know the relationship between them.
Okay, yeah.
Right,
yeah.
And then I have to wait until another update for CMake to come out in order to correct that. But of course, that means that I have a 2-week delay where no one can use my library. However, if I simply directly use the old variables again, it works fine.
Well,
are you aware of anything that they are doing to address this problem?
I mean, that's something that's completely tied to the fact that the CMake provides the Finder for you, and that it's decoupled from the version of Boost. They provide that as a convenience because at the time where the other packages did not. So I think it's more like a convenience thing, but that comes with the risk that any convenient Finder that's given by CMake will not be in line with the latest version of the package.
So you would not recommend me do this then?
Well, that depends. If Boost could provide a Finder, I would say use that. I'm not sure they do today because they use their own build system.
They do not.
So that's a tough choice. I would agree. Then again, I've started working with the guy at Conan because I really believe that package management is the way to solve all that mess.
Okay, thank you.
I'm pretty new to CMake, so this might be a really dumb question. But if you're writing a simple application, you depend on lib-A and you depend on lib-B, and both of them depend privately on Boost. And like Boost has, I think, 3 different ways you can build it into your project. Which component there, my app or lib-A or lib-B, is responsible for who owns that decision of how are you compiling the library in? Or does that depend, I guess, on how your Finder is implemented?
Okay. Well, technically speaking, I would recommend you to do your find, to run the find at the top level of your CMake list to make sure that you find only one version of every third parties. If you start splitting the finders, you will have 2 problems. First, you might not require the same version, and you might have like a diamond issue with 2 different versions, like it was just shown in this morning talk. The second problem you will have is performance. You will not see it with like 2 libraries, but where I come from, we had at some point a huge code base with CMake, and if everybody in his library, like 3 or 4 level down, is doing fine, you're wasting a lot of effort, especially because if you use some macros like project, CMake will not cache the results, so it will scan the file system like 1,000,000 times just to find the same library. So yeah, my recommendation is find at top level all the third parties to make sure that everybody agrees on what you use.
Okay, so ideally, the libs that you depend on, all they're saying is find package Boost, and the responsibility of how you find it and which one you
you can tell CMake when you do a find to require minimum version. It's possible, and then it will fail if it's not found.
Okay, thanks.
Great. Thanks, everyone.